So this video lesson is all about what to do when you want to find the GCF and LCM of expressions that have variables in them. Now this assumes that you're already familiar with and comfortable with finding greatest common factors and least common multiples. If you need a review of that, or if you're not, go ahead back to the GCF and LCM video lessons when we're talking just about integers, but we're going to start with the idea that you already know how to do that. So let's take a second and just quickly pause the video and go through and remind yourself how to find the GCF and the LCM of 36 and 40. And if it's been a while since we've done this and you're watching this, then I'll give you a quick start. So go ahead, pause the video, find the GCF and LCM, and then come back when you are ready to look at the answer and continue. So the first thing, of course, that we have to do with GCF and LCM is split our numbers that we're working with into their prime factorizations. 36 is 6 times 6, and each of the 6's are a 2 and a 3. So therefore, for 36, we have a 2, a 3, a 2, and a 3. For 40, 40 is 2 times 20. 20 is 2 times 10, and 10 is 2 times 5. So for 40, we have 2, 2, 2, and 5. So now, of course, in using the Venn diagram, and if you don't use the Venn diagram, give us just a second and we'll get to the other method of doing it also, is we have to put everything that is common between all of these numbers into the center. And so between 36 and 40, what they share are 2 copies of the prime 2. So those 2's go into the center. And then let's erase them from this side because we don't need them. We'll erase them from this side also. And so here we have our setup Venn diagram. Now remember that the greatest common factor is just the greatest number that is shared by both 36 and 40. We find the greatest common factor by finding all of the primes they have in common and multiplying them together to find that the GCF here is 4. Because that's 2 times 2. And now the LCM is just the collection of primes that we need to make both 36 and 40, not necessarily both at the same time, but it is the number that both 36 and 40 are factors of. And so we just take every prime that we see left and we multiply them all back together, which in this case you can go through and double check if you like, or you should have gotten 360 as your LCM. Now, if you are somebody who enjoys or prefers using prime factorization rather than the Venn diagram to find the GCF and LCM, we're going to go over that quickly now. If you are somebody who still prefers using the Venn diagram, that's great. Just go ahead and watch and remind yourself how this goes. But for the people who use prime factorizations, for 36, our prime factorization is 2 squared times 3 squared, because it's 2 2's and 2 3's. For 40, it's 2 cubed times 5. So when we find our GCF is the least number of each prime that we find. So the GCF is 2 2's, because between 2 2's and 3 2's, the least is 2. And then when it comes to 3's, 36 has 3's, but 40 doesn't, so they can't share any 3's. 40 has a 5, but 36 doesn't, so they can't share a 5, so the GCF is just 4. For the LCM, we take the greatest number of each prime that we find, so that would be 3 2's, 2 3's, and a 5, which does in fact give us 360. So that is our LCM and a review of how to do it both with the Venn diagram and with prime factorizations. So the question comes for this particular video lesson, what do we do when we have variables in our expressions? Pause the video for a second and go ahead and see if you can come up with an idea of what would we do if we were going to create a prime factorization for these. What parts multiply together to create 12x squared and 15x cubed. So go ahead and pause the video and see what you can do with that for a second, and then unpause the video when you're ready and we'll go over a way that we can think about it. So when it comes to 15x cubed, let's start at the bottom. When it comes to 15x cubed, we know that that's 15 times x cubed. Well, 15, we know, is the same as 3 times 5. So we can split the 15 up into 3 times 5, but there doesn't seem to be anything we can do with the x cubed other than maybe just expand it out into what it means, which is x times x times x. So it seems like the most we can do with 15x cubed is just to make it 3 times 5 times x cubed. So let's leave it at that for a second. And when it comes to 12x squared, well, we know that 12 is 2 times 2 times 3, so that's 2 squared times 3. And then for the x's, again, there doesn't seem to be much we can do other than maybe make it x times x or leave it as x squared, because there's not much we can do with that. And it turns out that once we've broken down the number part, called the coefficient of these monomials, which is a word we'll get to in just a second, and then leave the variables in their either expanded form or in their exponent form, we've actually done everything we can. So we're going to take a second and you're going to pause the video and write all of these things down. You're going to write both this and this. So pause the video, write these down, and we'll talk about them once you come back. So the first thing is that a monomial itself is just a number and a variable, or a product of numbers and variables. So these three terms down here, x cubed, or rather x to the fifth, y cubed, and x squared y cubed are all examples of things called monomials, because there is no addition or subtraction, it is just a multiplication of things. Other monomials include things like 12, because it is just a number, and it has only one term, and also other things like 3x to the fourth, because that is the product of numbers and variables. And so all of these things are called monomials. Basically, if it has addition in it, it's not a monomial. And then when it comes to treating variables and monomials, really they act exactly like primes. Without knowing what x is, we can't break x down into anything smaller. Without knowing what y is, we can't break y down into anything smaller. And so it acts exactly like a prime does when we're finding the GCF and the LCM. The most we can do for y cubed, for example, is just make it y times y times y. But often we just leave it as y cubed. So let's go back up to this example here, and we're going to find the GCF and the LCM of these two expressions, which is exactly what it is when we talk about it with numbers. So 12 is 2 times 2 times 3, and then we have two x's. 15 is 3 times 5, and we have 3 x's. So our goal now is to find everything that these two monomials have in common and put it in the center. Well, they have a 3, and 2 copies of the variable x. So now we're done with those. Our GCF is everything that's shared, which is just 3 times x, which is 3x squared. That's our GCF. And our LCM is just everything that we see, including all of the variables. So when we multiply all this together, 2 times 2 times 3 times 5 is 60. And we have 1, 2, 3 x's. So our LCM is just 60x cubed, exactly like we find it with numbers. It is everything that we see left in the Venn diagram. Let's do one more example, and then we're going to give you 3 practice problems to work on your own. So for this one here, and follow along, or pause the video if you like, but follow along. Here's our Venn diagram. When we find the prime factorization of 21 is 3 times 7, and then there are 3 y's. To be careful, because y's, if you draw them a certain way, look like 4's. And then 18 is 3 times 6, so 3 times 2 times 3. So no variables on the 18. So the only thing that these two can possibly share then is a 3, because they can't share a variable, they don't share a 2, they don't share a, let's make that look like a 3 and not a b. They don't share 7, and they don't share the y's. So what we have is this set up in the Venn diagram. This one also we will go over as a prime factorization for the example if you're someone who likes to do it that way. So the GCF is 3, because that's all we got. And the LCM, when we multiply everything all together, we take 7 times 3 times 3 times 2 is, I'll write it over here by the 18, 126y cubed. Excuse all of the random lines in this. 126y cubed, that is the LCM. So now, as I said, we're going to have 3 examples for you to work with. For each example, pause the video. Before we go back to do that, I promised a prime factorization here. So let's go ahead and look at that. 18 is 2 times 3 squared. 21y cubed is 3 times 7 times y cubed. For the things that, let's start with the LCM. The LCM is all of the greatest exponents for everything. There's a 2, a 3 squared, a y cubed, and a 7. All of that together, again, as we saw before, is 126 y cubed. And then our GCF is just everything, is just the lowest of each exponent. And because the 3 is the only thing that's shared, every other prime can get thrown away, and so can the y for the GCF. The only thing that they share is 1 copy of 3. So whichever method that you like, go ahead, pause the video, work through this example here, and see what you can find for the GCF and the LCM. Come back when you're ready to go over the answer. We'll use the Venn diagram for this one. 4x squared y is 2 times x times y. 5y cubed is 5y. So what they share, no numerical primes, all they share is 1 copy of y. So the GCF in this case is just y. That's our GCF. And our LCM is everything multiplied all together. So that is 20x squared y cubed. That is the LCM of that set of monomials. The next one, go ahead, pause the video, and see what you can do about the GCF and the LCM of 36x and 14x squared. Again, if we're looking in the Venn diagram way, 36 is 2 times 3 times 3, and it has this x. 14 is 2 times 7 with 2 x's involved there. So what they share, and we'll just cross them out this time, they share a 2, and they share an x. So this is the GCF, which is 2x. Then the LCM is everything that you see that's left. And so we have, for the numbers, we have 2 times 2 times 3 times 3 times 7, which is 252. And for the variables, we have 2 x's that we see, so x squared. 252x squared is the LCM. And finally, we have our last example here for you to look at. Find the GCF and LCM of 9y cubed and 8g squared. That is a g on the right, not a y. And so we have our Venn diagrams again, 3 times y times y times y. We need to get rid of those extra lines there. I'm not sure where they're coming from. And then for the 8g cubed, we have 2 times 2 times 2 times g, or rather the g squared. And so they don't actually share anything. There are no primes and no variables and nothing that they share. So the GCF is just 1. Just like it is if 2 numbers don't share any prime factors. The GCF is 1. Now let's take a look at the LCM, which is everything going on here. And so when we multiply everything together, the numbers come out to be 72. And the variables come out to be y cubed and g squared. So our answer for that, let's make that cubed look like an actual 3. 72y cubed g squared is our LCM. So again, when we're finding the GCF and the LCM of monomials, which are just expressions that have no addition and subtraction, just multiplication and numbers and variables, when we're finding the GCF and the LCM, we do it exactly like we do with numbers, except we have some variables, and in those monomials, the variables act exactly like primes, so you can put them in the Venn diagram or select them from the prime factorizations exactly like you do numerical primes.